Let's look at another example. Let's look at A equals 2032. So again, the question says, find all eigenvalues, if any, and corresponding eigenvectors of A, that's B. Is A diagonalizable? Yes or no? And if diagonalizable, find the diagonal matrix D and the invertible matrix P that satisfy A equals PDP inverse. And so we start. In order to find eigenvalues and eigenvectors, I need to set up the characteristic equation. To set up the characteristic equation, I need the determinant of A minus lambda I. To do that, I only need to subtract lambda from the diagonal. Some people use determinant lambda I minus A. Some books, some people, some resources on the internet. This also will give you a characteristic equation, give you the same lambdas. But I feel this is a little bit tricky because you will need to subtract the 2 from lambda rather than the lambda from 2. And you have to change the sign of the other entries. So it will become lambda minus 2, minus 3, 0, and lambda minus 2. And I feel this is tricky to remember that you will have to change the sign of the non-diagonal entries. So that's why I prefer determinant of lambda I minus A equal to 0. And of course, over here we do AD minus BC. This is 2 minus lambda times 2 minus lambda, that's 2 minus lambda squared, minus 0 equal to 0. This happens when lambda is equal to 2. Notice we only got one eigenvalue. We didn't get 2 eigenvalues. We got one eigenvalue. And the multiplicity of this eigenvalue, which we call the algebraic multiplicity from solving this, is 2. We have mentioned that before when we were dealing with the method of undetermined coefficients and so on. So like when we were trying to work with the characteristic equation of solving a higher order differential equation of constant coefficients. And you said that us knowing the repetitiveness of this root is called our algebraic multiplicity, which in this case is 2. Now I go to determinant of now what we have over here. 2 minus lambda, 3, 0. 2 minus lambda is 0. No, sorry. That's A minus lambda I times V1, V2. I go to the equation now is equal to 0, 0. So when I go to the augmented matrix, this is a redundant thing anyhow. If you notice, when you divide by 3 to get the reduced row echelon form, V2 has to be 0, but V1 can be anything it wants. And so our eigen space will look like the vectors T0, where T is in R, or in other words, it will look like T times 1, 0, where T is in R, or we can represent it, say, using the span of 1, 0. So the eigenvector that corresponds to this eigenvalue is equal to 1, 0, one representative. Now look at this. This is called the algebraic multiplicity. It's 2. This, how many independent eigenvectors do we get to represent this eigenspace is called the geometric multiplicity. Can I find any other eigenvector in this span that is linearly independent with that? No, I can't. This means the number of linearly independent eigenvectors here is only 1. And so the geometric multiplicity is 1. To come to part B, then is A diagonalizable? The answer is no. Because when the algebraic multiplicity is not equal to the geometric multiplicity, then we can't find, it's a 2 by 2 matrix. We need to find 2 linearly independent eigenvectors. We couldn't, we only found 1 eigenvector. And so we can't find 2 linearly independent eigenvectors, which means that we will not be able to diagonalize A. We say A is non-diagonalizable. And all these beautiful things that we talked about, diagonalization, would not work for us. Let's now increase our dimension. So we have been working with 2 by 2. Let's look now at 3 by 3. Another example, 3 minus 4, 16, 0, 6, minus 15, and 0, 2, minus 5. That's A. Again, I want to find the eigenvalues and the eigenvectors. And I want to check if it's diagonalizable. And if it is, I need to find the diagonal matrix D and the invertible matrix P, which satisfy A equal PDP inverse. So in order to do that, I start with the first step, which is finding eigenvalues. To find eigenvalues, I need to find the determinant of A minus lambda I. So 3 minus lambda, 0, 0. Minus 4, 6 minus lambda, 2. 16 minus 15 minus 5 minus lambda, which is equivalent to subtracting lambda from the diagonal. This determinant, I need to be solving it equal to 0. Determinants of 3 by 3, of course, are a little bit harder than 2 by 2, but lucky us, we can pivot the determinant along any row or column. And usually we choose the row or column that has the most zeros, because then our determinant will be easy. So if you notice row 1, three minus lambda times the determinant of 6 minus lambda, 2 minus 15 minus 5 minus lambda. Now, this is already a factor, so we keep it. Now, over here, we open bracket. We need to simplify this. We get 6 minus lambda minus 5 minus lambda minus 30, so plus 30. So minus 30 minus 6 lambda plus 5 lambda plus lambda squared. I don't multiply by this factor. This is already out. So I keep it on the side. I don't make things more complex by multiplying in. It's already factored. So I only try to factor here. And this minus 6 lambda plus 5 lambda minus 30 plus 30. So I'm left with 3 minus lambda, lambda, and lambda minus 1 in factored form. So what are the lambdas that might be solutions? 3, 0, and 1. 3 eigenvalues. When I have a 3 by 3 and I get 3 distinct eigenvalues, this means by default heads up, it's diagonalizable, because distinct eigenvalues give us linearly independent eigenvectors. And so by default, we will get 3 linearly independent eigenvectors, and this will be diagonalizable. Hide the heads up before even continuing. Now, for every one of those, I will now solve the equation. So now we can be faster. We can directly do 3 minus lambda, so 3 minus 3, minus 4, 6 minus 3, and minus 5 minus 3. This will be the augmented matrix from A minus lambda with the zeros, because we are solving a homogeneous equation. Now this is a row of zeros, it's out. All right, and we get over here. Now change this to 1 and revolve. I'll eliminate this and then change location, so this way. So keep it minus 4, 3, 2, 0. Eliminate this, multiply that by 4 and add. You get 0, 12 minus 15, 8 minus 8. And now divide by 1 and change locate by minus 4. So we get minus 3 over 4. 2 divided by minus 3 over 4, 2 minus 4, 2 divided by minus 4 is minus half. Divide this by minus 3, and then the row of zeros down. Now eliminate the upper one. I get minus 4. So multiply this by 3 and by 3 over 4 and add it, so we get 1, 0, minus half, 0, 1, 0. This means if this is V1, V2, V3, V2 is equal to 0, V3 can be anything it wants, and V1 will be equal to half V3. And so our eigenvector here will look like V1, V2, V3 equals T, half, 0, and 1. And so the eigenspace of lambda 1 equals 3. The eigenspace of lambda 1 equals 3 is the span of half, 0, 1. And so one eigenvector representative would be half, 0, 1, or if you want to get rid of fractions, it can be 1, 0, 2. That's the first. Now for lambda 2 equals to 0, I go ahead and do again the same thing. It will be A minus lambda I. So this is A again. And so A minus lambda I, the augmented thing will be 3 augmented, because when we subtract zeros, everything will stay the same. Now I will change this to 1, and then eliminate. Four of this. It's minus 16 of that. Now divide this by 6. Two over 6 is 1 over 3. And divide this by minus 15. You will notice, of course, one of the rows has to be redundant for us to have infinitely many solutions. So I'll get 1, 0, 0. Not both are redundant, 1, because now the third step would be doing minus R2 plus R3. Those will cancel, and so they will change into the zeros that form the redundancy for us. Now this is V1, V2, V3. This is the free variable. V2 has to be minus 1 over 3s, and V1 has to be equal to 0. Be very careful, V1 is not connected to anything. So V1 plus 0, V2 plus 0, V3 is equal to 0, so V1 is 0. And this means our eigenspace relative to lambda 2 equals 0. It will look like V1, V2, V3 is s multiplied by 0 minus 1 over 3 and 1. So it's the span of. And so a good representative would be V2 equals 0. If I multiply this by 3, this is my vector. And you can keep it like that if you don't want to multiply by anything. Come in, this can be okay, this can be a good representative. This V2 is not the same as this V2. This is a vector here, not a component. It's just saying I'm looking for the second vector, eigenvector, which can be also this. You choose, it doesn't matter. It doesn't matter. So now for the third lambda, which was lambda equals to 1. We now need to solve 3 minus 1, 6 minus 1, minus 5 minus 1. Again, this gives me 1, 0, 0. minus 4 plus 2 of that, 16 minus 8 of that. You notice this is minus 3 of that, so it's redundant. So we get 1, 0, 0, 0, 0, 1, 2 over 5, 0, and redundancy for the third one. So this means again V1 is 0, V3 can be anything at once, and V2 will be minus 2 over 5t. And so V1, V2, V3 will look like 0 minus 2 over 5 and 1 times t, where t is any real number. So this means the eigenspace corresponding to lambda 3 equals 1 is the span of 0 minus 2 over 5, 1. And this means that a good vector representing that would be either the same one, or if you don't like to work with fractions, you multiply this by 5. You get this answer that we have over here. Notice that the three vectors we got, 1, 0, 2, and 0, minus 1, 3, and 0, minus 2, 5 are definitely linearly independent. They are not related at all. And so this means A is indeed diagonalizable. And in order to diagonalize it, we have lambda 1 equals 3. It gave me V1 equals 1, 0, 2. Lambda 2 equals 0. It gives me V2 equals 0, minus 1, 3. Lambda 3 equals 1 gave me V3 equals 0, minus 2, 5. Three distinct eigenvalues give me three linearly independent eigenvectors, and this means A is diagonalizable, with D being the diagonal matrix with our lambdas being on the diagonal, lambda 1, lambda 2, lambda 3, and our invertible matrix P would be made of our eigenvectors. This is lambda 1, this will be V1. This corresponds to lambda 2, this will be V2. Lambda 3, V3. So that's why many people would have different D, different P. It doesn't matter. Some people would have different order here, but then it will be reflected with different order here. So the answer will still in total be the same. A is going to be equal to PD, P inverse as such. Let's look at one more example. A is 4, 2, 2, minus 2, 0, minus 2, 1, 1, 3. Again, find the eigenvalues, eigenvectors, and find bases for the eigenspaces of the matrix. To find the bases means you have to find all the linearly independent eigenvectors representing the space for the eigenvalue that you are working with. Let me explain that. So if I go back to this example that I just solved, we say that 1 over 2, 0, 1 is a basis for this eigenspace. The vector 0, minus 1, 3 is a basis for this eigenspace. The vector 0, minus 2, 5 is a basis for that vector, because every vector here can be written as a multiple of that. And so this is one vector only, so by default it's linearly independent, so it forms a basis for the eigenspace that we're talking about. So now over here, again, I need eigenvalues. So I need the determinant of I subtract lambda, and then I'm just using row 1. To expand. So now it's not like the previous problem here. I have to multiply them all. So here 4 minus lambda minus lambda 3 minus lambda plus 2. Put them in big brackets. That's first. 2 bracket 2 times 3 minus lambda minus 2 plus 1 big bracket minus 4 plus 2 lambda. Now this needs algebra. Now simplify. This has to be expanded. So I get minus 12 lambda plus 4 lambda squared first minus lambda cubed, then plus 7 lambda squared, then minus 16 lambda, then 12. 8 plus 8, 16, minus 4, 12. Of course, when it becomes 3 by 3, we expect we'll get a cubic characteristic equation. 4 by 4, a fourth order, يعني quartic characteristic equation. The power of the characteristic equation is always equivalent to the dimension of the square matrix that we are starting with, of course. And now, so this is a cubic equation. Now we solve it. You use mod 4 on your calculator if you don't know how to solve this mentally. Usually mentally, we think if we want to solve a cubic equation, then the one of the roots would be dividing 12. So it will be plus, the options are those. Because 1 times 12, 2 times 6, and 3 times 4. Those are the options that divide 12. Plus and minus 1, plus and minus, and you check them. And when you get one root, you divide by that root using long division to find the other roots. This is one of the options if you don't have a calculator. Now the second option, if you do have a calculator, you'll get that you have only 2 roots. The first lambda that you will get will be equal to 2. And the second lambda will be equal to 3. Only 2 roots. Usually cubic equations have 3 roots. So what happened here is that we got 2 real roots over here. This means what is the third root? The third root has to be one of those with multiplicity 2. That's why if we use this method and we divide, we'll be able to factor it properly, and then we are able to find which one has multiplicity 2. But to be honest, I don't care. You tell me, I need to know the algebraic multiplicity of this and that to know if it's diagonalizable or not. See, yes, this will help us know if it's diagonalizable ahead of time. But if we don't know how to factor this properly and we don't know how to get the algebraic multiplicity, the one that will really spill if we can diagonalize or not is getting the eigenvectors. And once we get the eigenvectors, if for any one of them we got 2 independent eigenvectors, this one would be the one with the multiplicity 2. If we got this and this had one eigenvector only, this means one of them had multiplicity 2 but got geometric multiplicity 1, which means it's not diagonalizable. So let's work out for each one of them to see what will happen. So for lambda 2 equals 2, for lambda 1 equals 2, we get A is, to start with, 4, 2, 2, minus 2, 0, minus 2, and 1, 1, 3. And so A minus lambda I would be 4 minus 2, 0 minus 2, and 3 minus 2. Now we need to reduce it to reduced rational form. If you notice, the 3 rows are the same, which means this is redundant and this is redundant to the first. So if you divide the first, if you just do minus row 1 plus row 2 will become zeros. And if you do minus row 1 plus row 3 will become zeros. And then divide row 1 by 2. This means I have 2 free variables. This is the leading one, and those are free variables. V2 is free, and V3 is free. This means V1 will be equal to S minus half T. And this means our eigenvector is nothing but V1, V2, V3. This means if we split, we'll get 1, 1, 0 S and minus half 0, 1 T. This means for S is equal to 0, we get and T equals to 1, we get minus half 0, 1 as an eigenvector. And for T equals to 0 and S is 1, we get 1, 1, 0 as an eigenvector. So this means we get 2 linearly independent eigenvectors, because what is our eigenspace going to be looking like? Our eigenspace is going to be looking like the span of 1, 1, 0 and minus half 0, 1. This means one eigenvector could be 1, 1, 0, and another eigenvector could be minus half 0, 1, and those are linearly independent. This means that if we go back now here, we know the algebraic multiplicity of this is how much? 2. And how much is the geometric multiplicity? As well, 2. Because the algebraic multiplicity has to be either equal to the geometric multiplicity or bigger than it. So geometric multiplicity is always less than the algebraic or equal to it. So for this to be 2, this means the algebraic multiplicity has to be 2 as well. It cannot be anything else. So over here, all right, this means I got 2 eigenvectors corresponding to that. Now I go to the second eigenvalue. The second eigenvalue is lambda 2 equals 2, 3. And so again going to A, which is 4. And getting A minus lambda I. 4 minus 3, 0 minus 3, 3 minus 3, augmented. I always forget the zeros because they are redundant, I do. So I always write them so that you'd know what we're doing. And now, if you notice, this is already 1. Use it to eliminate below. So 2 minus 2, 1, minus 1, 2 minus 2. If you notice, this is equivalent to that. It's to twice of that, so you can see it's redundant. Now eliminate above by adding twice of row 2. Which means that those are leading ones. This is a free variable. This means our eigenspace corresponding to lambda 2 equals 3. Is the span of 1, 1, 1. So how many eigenvalues did we find? First, how many eigenvectors did it give us? 2, which are, again, 1 1 0 minus half 0 1. And the second eigenvalue, it gave us a third eigenvector. 2 from here, they are linearly independent. The third from here, that's also linearly independent because it comes from a distinct eigenvalue. This means we have 3 eigenvectors that are linearly independent, which means A is diagonalizable. D would be lambda 1 counted twice because it gave me 2 eigenvectors, and lambda 3 counted once, and P would be made of 1 1 0 minus half 0 1 and 1 1 1 over here. A will be equal to P d P inverse. All right, the last thing is coming next.